Now the second part. So memory grids, higher level abstraction, agentic memory. So we call it as agentic memory. It is a higher level abstraction. So a lot of intrinsic data to the low level implementation is abstracted with our agentic memory concept. In agent grid offers a 5 types of cognitive memory abstraction library that gives AI agent a structured, queryable, and semantically searchable memory system. So this agentic memory will abstract the usage of the DBs below it. So what are those 5 kinds of no abstraction layer we have provided? We have episodic memory, we have semantic memory, procedural memory, reflective memory, and reward memory. So these are the 5 level of abstractions we have provided. And so I'll explain in detail with an example what these individual memory systems are in short. So episodic memory, it's a time bound event and session logs. So it basically uh, you want to store something like what happened just now, what happened yesterday. So you want to store any raw data, right? So this you can use the episodic memory. Semantic memory is for a knowledge graph facts stored as a subject predicate object triplet. So basically a truth, you want to store know the world knowledge about anything. So you will be using this particular semantic memory, where you will be using a subject predicate object kind of a triplets. And also next is a procedural memory, which is an reusable skills. Procedure here is a process. So you might have some detailed process, like if in case you want to do something, you will might have some steps that you want to run. So for that, we call it as like reusable skills with ordered steps. How do I do this? So in such cases, you have to use this procedural memory. And if you want a reflective memory, here it is nothing but if in case agent wants to compress the memory that it has got with its past experience. uh, what did I learn? Basically, it has done some task. It wants to condense it. It wants to store it for a longer time. Then you will be using this reflective memory. Basically, it gives you past experience in a condensed fashion. And a reward memory, where it's about reinforcement learning. So you will have a triplets here: state, action, reward. Here it was a subject predicate object, whereas here as state, action, reward, feedback. So what works the best? So here a feedback is required from the user. Whenever it does a good, you have to give a feedback, and it will be stored so that it can use this memory to do a better job in the next transactions or next sequences. So all these memories we will discuss in detail with an examples, and also we have an example code to run it, and also I have an agent code to showcase. So agentic memory, we have 5 types of agentic memory, and all these 5 types of agentic memory is backed by either of this DBs. So either or all of this DBs. So VV8, ArangoDB, and a Postgres SQL. So as we mentioned that you will get a structured, queryable, semantically searchable. So structured here is to give the structure to the data. You have a Postgres SQL, and also we can do an queryable, definitely, because anything you have, you can query it. In also on MemoryGrid you can query it. And semantically searchable memory system. So you have a VV8 for a semantic search. Semantic here is nothing but a similarity search. So that spans a 5 cognitive distinct memory types known as episodic, semantic, procedural, reflective, and reward memory system. So that's whatever I have explained in the top, it is available here, but we'll get into in detail. So the architecture, every memory record is written to all the 3 backends simultaneously. So whenever you dump something in one memory, so without your knowledge, those data will be getting stored in either of this DBs. Most of the time, it is all the DB, and certain occasions only certain DBs might be skipped. So PostgreSQL, it will store a structured data. You can do exact lookups because it's a structured data. You can directly go with your key searches. You can do filterings. You can do aggregate. So all such things you can do. It will use the PostgreSQL. So for the semantic similarity, it's a VV8. It will use the cosine similarity search, and it stores embeddings in a user defined dimension. Right now I have mentioned as 384, but it can be defined. User can define it. And ArangoDB, graph nodes plus edges. If you want to store anything, the nodes and edges, then this is the ArrangeDB, and also it will help you in relationship traversal. So these are the main 3 DBs which powers our agentic memory. So reads use most appropriate backend per query type. So whenever you use any APIs that are provided as a part of this agentic memory, they know it which DBs to use. Let's say you are asking for retrieve of some ID. So ID here is a one single key which can be directly accessible in the PostgreSQL. So it goes to PostgreSQL database and gets the exact primary key lookup. Whereas if you say you are using a search and your query is a string, then it understands that it has to go to the VV8 for a vector similarity search. And if you provide a top k, then it will bring the top k items from the VV8 DB, and from that you need to do a hydration. Hydration here is basically, so once you get the top k, let's say top 5 items you got, you will get individual IDs from that, and from that individual ID you go to the Postgres and get the more information about those IDs, because in the VV8 in the VV8 you will have only the embeddings, you will not have any other details, any other extra metadata will not be there. So you go and search in the Postgres so that you get all the details about that DB, like what all different things are present in that particular vector similarity search item, right? So whatever you have extra things, you will get it from the Postgres. So that we call it as hydration. And graph queries, like you have any traversals, any graph node edges searches, right? So in such cases, a ArangoDB AQL traversal will happen. So we'll have again these are the libraries. We'll check this in detail. I have examples, very structured examples. So these are the library requirements, and you don't have to install it because it will be available in our MemoryGrid examples. So you can go to our GitHub. Our GitHub is present in uh, Open Cyberspace, Cosmos AI AgentGrid. In that we have posted the codes for several of our agentic library usage. So we have service grid workflows, agentic patterns, and a memory grid. Right now we are in memory grid. So so you don't have to install it because I have already provided in memory grid examples, and you have a agentic memory here. So this itself you can directly straight away use it. So here is a sample code that I'll be explaining later with an examples. Like I'll again come back to this. I have a better examples than this. This is just the first readme. So I suggest you to go to docs folder, and if you go to docs folder, there is a API reference.md and concepts.md. So after reading this article, I mean this readme.md, the main readme.md, I request you to go to docs and check these two files. These two files gives a little bit elaborated details related to the each 5 DBs, and this will give you an API reference of those DBs. So deployment.md is related to about the deployment, because it requires these DBs, right? How to deploy them will be available in the deployment.md. It's for a deployment sake. And implementation.md is for a developer who wants to contribute to us. So how this memory is implemented behind the scenes. So you want to know about that, then you can go and check this implementation.md. But if the user if your task is just to use the memories, then these two is now concept.md and API reference.md. So I have opened the concepts.md and API reference.md. So let me just go to the concepts.md, and we will get started with each and every memory. So we have agentic memory. So models 5 cognitive distinct kind of knowledge that intelligent agents need. Each type of captures something fundamentally different. So not just a different data shape, but a different. So it could be relationship between the agents and what it knows. So basically, it could be any. They are basically fundamentally different data. They will they will store. So first is episodic memory. So it basically answers what happened. So any transactions, any small events you want to note down, so you can use this episodic memory. So what it is? So memory of specific event bound to a point in time or a context. So this agent, it's in like a agent's diary, a raw data. You can store it, a time-stamped experience tagged with who was involved, what happened, and how it turned out. So any such details you want to note down about your recent transactions, right? Whenever agent is doing some transactions or agent is doing some activities, so you can note down related to those transactions in our episodic memory. So what are key fields? You have a session ID, agent ID, session ID, agent IDs are string. So basically which conversation or session this belongs to. It is basically unique representations, and which agent this is recording. So you will have a agent ID, which is nothing but a subject ID. So you can use those subject IDs to create a agent ID here, and a context. So context is a free form dictionary. It's a Python dictionary. You can store anything. There is no like hard keys. We have yeah, mandated. So it's a free form. You can give any keys, and a outcome. So outcome is an enum value here. It has a success, failure, neutral, unknown. These 4 states are present. So anything you can set it. So, and also the importance. So importance is basically a score, 0 to 1. So basically 0 to 100%. So how significant this episode was. So if it is very important episode that you don't want to forget, then you give an higher memory. Or if it is okay, you can forgettable, you can give an lower confidence. So that with this we can always do a filtering operation, or a querying operation, which is the highest important, which is a low important. So all those things we can query it. So a human analogy for this particular episodic memory. Last Tuesday, I tried to book a flight, and the payment failed. So it just something happened last Friday, and I just want to retain this in my memory. So uh, there is nothing learning from here. It is just that I just want to note down. I don't want to derive any extra other things from this. I just want to note down. So in such cases, you will be storing this in a concrete, singular, time anchored, not a general rule. It is not a general rule. It is just scratch pad that I want to note down something. It's not a skill also. I just want to, it just happened that, and I just want to store it. It's not a skill. So you don't have to, use it as a skill of to do something. So it is not a general rule also. It is not a world memory also. So it just you that something has happened, you want to note down. So that's what the human analogy of this particular memory. Now, why agents need it? Without a specific episodic memory, every session starts cold, meaning if you don't note down your experiences, so you will be lost. Anything you have done a transaction, if you don't want to note it down, it will be lost somewhere. So again, you will not get those details again. You are because agents will not store it anywhere. So if in case you want to recall your prior interactions, like say anything happened uh, past days during the flight booking, or if user is saying, say, I'm booking it again one more another time. So in such cases, you can recall what was happened, right? So to do that, you can use this particular memory, recognize recurring patterns per user or session. Because let's say in the session ID you have got a failure, again in the same session ID again you are getting a failure. Basically in the same session ID you are getting 2 times of failure. So it's basically puts you into a situation that why you need to investigate why the failures are happening. So learn from the past failures without re-experiencing them again. So this is what this is why this memory is required as a scratchpad memory. So what it enables, beyond basic storage, you are not going to simply dump it, but you need to retrieve it as well. So beyond the basic storage, you can do a filter by session IDs, or filter by the outcomes. You can search all the failures, all the successes, all the unknowns, all that way you can filter out. Filter by importances. So basically the importance is here. You can give you can ask for give me the top 5 important things that we have in the episodic memory. Then it can give filter by the top top importance. And also you can link episodes to each other, meaning like let's say this last Tuesday I tried booking a flight, the payment failed. So I can basically if you want to know, I can break this also into episodic memory. Payment failed for last flight booking. This is one payment failed is one let's say one episodic memory. And the payment failed because of the last flight was a horrible experience. The last flight booking was a horrible experience. This is one episode, and payment failed is one other episode. You can link those two episodic memory with the help of ArangoDB edges. You can link those two episodes. Linking of episodes, causal chains of episodes is also possible. Or else follow up what follows what follows the episodic memory 1 led to episodic memory 2, something like that also you can note down. So link episodes to the reflection they generated. So later on I'll explain this later on. So we can use this episode somewhere else also in other memories, so I'll tell you. So this is about the episodic memory, basically a scratchpad, a raw data. You want to store any transaction data, time bound events you want to note down, you will be using this. So next is a semantic memory. So what is true? So the truth, the if you want to store any truths, so then this is the one. A structured knowledge base of facts stored as subject, predicate, object, triplets. So you have a triplets here: subject, predicate, object, the standard form of a knowledge graph. So this is how the knowledge graphs are stored, and this is the agent's world model. A context tree, you don't have to too much of context you need to provide, you just have to provide these three things: truths that do not belong to any specific event or do not decay with time. So you need to give a context free truths that is not going to decay, or that's not it's not an event that you have to forget, right? So in such cases you need to retain it. It's a truth that is has to be stored for this particular agent. In such cases, uh, not just for this particular agent, any agent in the entire agent agency. So you can use this particular memory. It's about a truth, so you need to give a subject, predicate, object, and you need to give a confidence as well, which is a floating point number, and also a source. So predicate here is a relationship property. It's basically an edge. So source here, basically you will have a string, right? So from this string you would have derived. So like Paris is capital of France. So this is the string that you have got in your transaction, and from this you are trying to extract a subject, you can extract a predicate, and you are extracting an object, and that you are storing it. And this is the source of it. So this, because of this source, you have created this subject, predicate, object. So it is a string, it's a free form string. It's a fact that came from. And let's say human analogy: water boils at 100 degrees. So Paris is capital of France. So these are the truths. So these are not memories of a specific moment, they are stable facts that survive independently of any particular experiences. So in such cases you will be using this. So what agents needed? Why agents needed? Agents operating in complex domain needed a grounded factual knowledge that persists across the sessions. So here in our earlier memory, we were using sessions and agent IDs, right? Here we are not using those, because this is a truth, world truth. I want to store it. So in such cases, we'll be using this, and it can be queried relationally, semantic. So relational querying is very important here. And also semantic memory answers questions like, what do I know about Paris, or what entities are connected? I'll give these examples later. But let's say you have you want to check what do I know about Paris. So Paris is France, France capital. So whenever you have this kind of questions within the agent, definitely it can check the this semantic memory. So without replaying the experiences, I mean, you don't have to check all your past experiences again, but you can use this memory to check the the answers for what do I know about the Paris from this particular memory. So what it enables beyond basic storage, it enables triple lookup. So you can find all the facts, you can query all the predicate also, and or you can query all the triplets also. So you can all the querying of the facts, querying of the subjects, querying of the querying of subjects, querying of a predicate is possible, and querying of a triplet is also possible. Confidence based filtering is also possible, because you have thresholds here, right? Confidence, that also filtering is possible. Knowledge graph, so traversal, find the shortest path between two entities. So this is also possible when you store a subject, predicate, object, right? So you can query the knowledge graph traversal as well. So neighboring lookup, who is neighbor of this, or what is directly connected to X. Let's say X is on episode, X is in one memory, and you want to check who else is connected to this particular memory. In such cases, you can use this particular this particular memory. Auto construction, storing the fact automatically creates the entities, nodes, and edges between them. So you can create a the automatically storing of the facts can give you this nodes and edges. So as you can see, this will definitely use the ArangoDB in the backend. Along with it, these get stored in the your um, the, the PostgreSQL as well, and also the source, since it is a raw string, this can get stored in the VWait as well. So similarly here also we'll use all the until unless you are linking, right? Here I have shown you that you can do a linking also. If you are not doing linking, if you are just storing this, all this data will get stored in PostgreSQL, as well as it will get stored in the PV8. So so next is the third memory, procedural memory. How do I do this? So basically you want a process. So if agent wants to have a process of doing something, then you can use this particular memory. So what is this? So memory of skills. So till now it was not about skills, but this is here it is a skills, a named ordered sequence of actions with trigger conditions. So you need to provide a name, and it will give, you have to store the ordered sequence of actions, and you need to provide the trigger conditions as well. So whenever trigger condition occurs, then it searches what all those orders of sequence I need to implement, and the agent can implement those order of sequence. So this is know how rather than know what. Each procedure is reusable recipe the agent can recognize by description and apply it step by step. So we'll see what all things are there. Name, there is a name string, a human readable skill name, because it's a named. Trigger conditions, a list of strings. As we mentioned, here is a trigger conditions are required. It's a list of strings, natural language description of when to apply this, and the steps. So steps is also list of procedure, list of a procedure step class. So it is also a list. You need to have procedure 1, procedure 2, procedure 3, and this each procedure is again an action, parameter, expected outcome. So these three things has to be there as a step. So this has to be stored as a list in the list of procedure steps in the steps. So next, success rate. So float 0, 1. Basically, it's a rolling average across all the recorded executions. So whenever, let's say, agent has executed this procedure, it has seen a success, then you have to call this increasing this success rate. Basically, it will increase the rolling average of the success across all the recorded execution, not time based, it's all the record execution. So rolling average happens across all the records. So use count, so basically to increment the count, like how many times this this skill has been used. So for that we'll use this particular variable. So what is human analogy here? A surgeon knowing how to perform appendectomy. So this is a procedure. There's a procedure whichever is the patient, so you need to take care of the proper process here. So that, if it is in such cases, you require such kind of steps, right? So you need to use this particular memory. So it's a muscle memory skill, not a specific event. So last Thursday I performed one. So there's a big difference. Last Thursday I performed one, and how to perform appendectomy is a big difference, right? So to answer that, how to perform, what is the steps, so we'll have this particular memory, and not an abstract fact. Appendectomy is remove the appendix. It's just a fact, it's a fact. So but here it is not a fact, it is a procedure. So it's a procedure. Step 1, step 2, step 3 will be available. So let's say in this procedure, if a patient is a BP, blood pressure patient, how it has to be done, there will be procedures. Sugar patient, so definitely they, in the medical terms, they will have a different process to follow. So why agents need it? Agents often face recurring task patterns, procedural memory, because since agent will be doing some sort of a task, it might see the same task again repeatedly coming again and again. So in such cases, you can put this into a agent's memory. Procedural memory lets them store and retrieve the workflows by semantic similarity, and I need to send a report. So whenever user agent derives this particular thing from the user's input, let's say user is asking for sending a report, it means agent has to ready for sending a report. To send a report, it matches a send email named skill, so it can use the that particular skill. So then track whether the skill is actually works via its rolling success rate. So if that worked and user also said the mail is sent, then you will increase the success rate. So what it enables, beyond basic storage, you can do search by trigger conditions, because here trigger conditions is list of string. You can always do a semantic match, not exact string, it can be semantic match. Record execution, and you need to pass a success. Here with nothing but you are updating the rolling average. So if you call this function, rolling average will be updated. get top procedures to get the top reliable skills in the given domain, and get by name you can get by exact by giving the name as well. And steps are stored relationally, separate table with the foreign key, and always retrieved in order. So whatever the steps you store, they are stored as a foreign key in the database, and it is always retrieved in order. So you can have different sort of a processes. Those procedures we cannot store it in a PostgreSQL structurally, but we'll use a foreign key for that, because one let's say one skill has 10 steps, one some other skills has 15 steps. So putting it in a skill is difficult, so we will use this FK foreign key concept. So reflective memory, what did I learn from this reflection, self reflections? So because of some transactions you would have learned something, or because of several transactions of same similar transactions, you want to compress them, or you want to get one good information out of it. So in such cases, a reflection out of it, you will be using a reflection memory. So reflective memory, self-generated insights and lesson distilled from the past experience. So you have several you have done several transactions, you've got several experience in it, and you want to distill something out of it, you want to learn a lesson from it. Unlike episodic memory, which is just storing the raw events, reflective memory is a agent's interpretation of those events. So it is a metacognition turned into stored reusable knowledge. So something is getting inferred from those past experiences, what this reflective memory. So we have seen the episodic memory where we will store raw. Semantic memory, or ground truth, a truth will be stored. A procedural memory, a skill will be stored. A process will be whatever the process we need to follow, it can be stored in the procedural memory. Whereas reflective memory is a self-learning. So a distilled fact, distilled knowledge um, from the past experience is what will be can be stored in the reflective memory. So here, lesson learned. So basically, a string. It's a distilled actionable insight. Uh, Improvement suggestion. A specific change to make to future behavior. It's again a string. You can give improve suggestions. What is the lesson learned? How to improve the lesson, to improve the lesson learned, what you need to do. So that can be put here. Source episode ID. So this is what I was saying in the episodic memory, link episodes to the reflections they generated. So basically I can use this particular episodic memory, and I can link this to a reflective memory here. So that's what the source episode ID is, the episode that generated this reflection. So basically, you have several episodic transactions. So from one transaction, you would have learned something. So you can give a that particular source episode here. So so what is the lesson you learned, and what is the improvement you need to do whenever it comes in the next type? So in next time you have to give an improvement suggestion. So confidences and applied count. So confidence is again how certain this agent is about this lesson, and applied count is how many times this reflection has influenced a decision. Meaning, to take this particular lesson and improvement suggestion, how many times this uh, how many times basically this reflection has influenced the decision. That's what this applied count is. So human analogy, after failing at a task, thinking I should have asked for a clarification first. Meaning, let's say agent has asked something, but you have, without a clarity, you would have given a response back to the user. In such cases, if user has given a feedback to you that it is not good, maybe you could have asked a clarification to instead of taking a negative feedback, you could have acted upon those negative feedback, and you can update your learning from it. So that's where this kind of this is the human analogy of that reflective memory. So that meta observations generated by a person, not recorded from the external events, is the reflection. Basically, user giving a feedback, and with that feedback you would have learned something. So it changes the future behavior without being a procedure. So it's not a procedure, it's not a fixed steps, right? So but you don't have a fixed steps here, so you have learned it. So, and also it is not a fact also, so you just learned it because of your experience. So it is a universal true, just true for, it's not a universal true. Whereas the episodic memory, sorry, the semantic memory was a universal truth, whereas here it is for this particular reflective memory is this particular agent only. So it has learned something. So it is just true for this agent in this context, because because same task can be done by multiple agents but in a different context. But for this agent, this is the a truth for it. So it may not be the truth of the no the world truth. It is just the truth for this particular agent. Why agents need it? Episodic memories accumulate endlessly, and reflective memory is a compression layer of it. So this is very important. So you can put anything in raw memory into the episodic, but reflection is a compression layer, extracting durable, actionable lessons to the agent. Does not have to re-examine every past failure. This is very important. So once you compress the all your episodes, or once you get a proper reflection from it, it's basically you have learned a good lesson. So applied count makes this one memory type that measures its own influences. So how many times this got influenced. So this is the applied count. So what it enables beyond storage, mark applied. So increment the influence count each time this lesson affects the decision. So basically we're incrementing the applied count here. Link back to source episodes, ArangoDB. It uses the ArangoDB and it uses the edge known as episode reflection edge, preserves the provenance. So basically you're giving a source episode, right? Whenever you do a source episode, so basically it creates a link in the ArangoDB with this particular edge name. And get most applied, get from episodes. So this can be queried. Confidence filtering, that is also possible. So this is fourth memory, and the fifth memory is a reward memory. So what works best? So here what I learned, and here now this fifth one is a what works best. As the name suggests, reward. So it is kind of a a reinforcement learning style. You have a state, action, reward. So again one more triplet. So you had a triplet in the semantic memory. Again you have a tuples here. So state, action, reward, tuples, and each record says when I was in this state, took this action, and I received this reward. So when I was in this state, I did this action and I received this particular reward. So in such cases, you can use this particular reward memory. The store can then recommend a best action for a new state by finding a past states. So this is where you would be using this. So for a retrieval purpose, this is the line. The store can recommend best action for a new state by finding similar past states. So you have stored your reward memory, and you want right now you have one state, and you want to take an action, which is the action, and which if you take which action you will get a better reward. So then you can use this particular queries of this reward memory. So key field, state description, it's a string, natural language description, action, which is again the what is the agent, what agent did, and a reward, upload numeric outcome signal, positive, which means a good, a negative means a bad. So outcome, again optional description, outcome label, it's a string, so you can give a description to this particular label that we have. And a policy is like a namespace, named strategy grouping, multiple policies can coexist. So it's just like a namespace to define I mean give up boundaries to each reward memory. Let's say in your uh, uh, booking of financial transactions, you can create one reward memory where financial transactions related to flight booking, train booking, or a movie ticket booking, anything can go inside that particular namespace. So it's basically a policy, a namespace or a policy. We call it as, we can separate it. In the same policy, there can be multiple rewards as well, multiple reward memory as well. So context, key value pair, a dictionary, additional state information you can store in the context. So human analogy, a child learning that I'm a hungry and I ask politely, I get a food. It's a +1. So a state, action, a reward. Versus when I demand it, I get scolded. So this is a -1. So if you uh, when you are hungry, if you are demanding it, then you get scolded. So it's just one learning that the child is about to take. Over repeated experiences, the reward signal shapes the future behavior of future behavior in similar situation, not via rule, but it via accumulated evidences. So it's about accumulated evidences only. This experience is going to build for the kid. So why agents need it? While reflective memory captures qualitative lesson, because this memory, the fourth memory that we have talked, gives you a qualitative, but here you will get a quantitative because we have a reward in the we have a rewards here, reward system here. So quantitative feedback, it enables behavior shaped by empirical results rather than explicit rules, and supports multi-policy learning as well. So that's what I mentioned. We can see in the same policy, you can have a multiple learnings. An agent can maintain separate reward spaces for a different behavioral objectives. So yeah, that's what I mentioned, like it's like a namespace. So what enables beyond this basic storage? Get best action. You can give a state, get best action. Vector search for similar states, because the state is a similarity, a big string or a string. You want to search what all other similar states, the best actions for this kind of a raw state. So in such cases, it goes to a vector similarity state and returns the actions with the highest average reward. So best action stats. So you give a policy per action, count, average, max, min, reward from the Postgres aggregates. You will get the Postgres aggregates for the given policy namespace. You can get the summary also of the policy namespace, overall statistics for a named policy, record transaction. So from ID to ID and action. So build a state transition graph in ArangoDB. So you have a from ID, you have a to ID, and you have a action. Let's say you have some um you have some IDs like again, this from ID to ID is nothing but from any of the memory you have. So and also action, what action you need to take. So that's what you are going to record the transactions. So here again, for a transaction, since it is a from ID to ID, it goes state transition graph. So we use ArangoDB here, and I guess get successors states. So traverse reachable state from a given state. So this again leads to traverse path finding. So success states. So these are the APIs present in the reward memory. So we'll see one examples. So I have a API reference in here. So before going to API reference, let me just open the examples. So I have examples here for all the memory. I have examples. So example episodic, example procedural, example reflective, example reward, example semantic, and also I have if in case you are not a OpenAI, if you want to run any other embeddings. So right now I might be using an OpenAI embedding here. If in case you want to run any other embeddings, you can use this particular file to understand how to send a embedder. So let me just show that first, because we are using a we need to send a embedding as well, right? So here as you can see, yeah, so first let me just go to this examples. So we have to import the Python libraries. Agentic memory, agent memory is a class you need to import. And also this is a enum, outcome is a enum. So I'm running with agent memory. I need to initialize that some configurations here. The configuration I'll show you later on. And I'm using a with basically a context. So as soon as we come out of this particular block, all the memory connections we did will be terminated safely. So that's why I'm using a with. So with context, or else what happens is you create this without the with, then whatever you have created the agent memory object, right? Again, you need to call the termination also. So instead of that, you can directly call the with as a mem dot remember episode. So this is for a storing of a episodic memory. So we have a episodic memory, the first kind of a memory. So to store the any episodes, what you need to do is, for storing of episodic memory, you need to provide session ID, agent ID, context, outcome, importance, right? So same thing. So context, sorry, the session ID, agent ID, context. So this is the uh, session ID is there, outcome is there, important is there, and one other thing is importance, outcome, context. So another thing is missed here. So that's nothing but the raw data. So we can check it from the API. API reference. So let me just show you the API reference for this particular episodic memory. So you are storing So this is an let me just go to the example itself, so that I can show you the direct example. So episodic. So here at the top we are just importing the live we are loading the env. So whatever the env file we have, I'm just loading it because I have API keys in it. And these are the agent memory and outcome. As I explained, we have two classes that you are importing it. So I'm copying all the configurations. This configuration file I have here, dbcleanup.py and dbconfig.py. In the dbconfig, so you have you're basically constructing the configuration required for each of the memory. We have a Postgres, ArangoDB, VV8, and also Redis. So all those uh, things are read from the env file, and you are creating a memory config. And that memory config is what I'm trying to get it here. The CFG is nothing but the object of this particular memory config with all these details reading from the env file. And then I'm passing agentic memory CFG, and I'm passing the OpenAI key here. This OpenAI key is present in the env file. And since I'm giving an OpenAI key, it means I will be using a OpenAI embedding for it and a memory. So I'm creating a memory object, and from this memory object, remember episode, I'm giving a string, and I'm giving a session ID, agent ID, and context. Context is any free form dictionary, and the outcome.success. This outcome is enum that we have it here, and the importance. So basically, right now I'm putting some strings here, and I'm giving a confidence here. But actually, you need to derive it. The agent has to derive it, either talking to the LLM. Hey, this is the transactions, and what I have a episodic memory like this. It requires this kind of structure. Um, Give me the data required for this. So this is the string that I want to store. uh, Session IDs, anyway, you will have it from your side. um, Agent ID is also basically a subject ID of an agent. The context also, you can basically you can check this and this from the LLM itself to format the data. So LLM will format that and give it to you, and then you can store that in a episodic memory. So if you print e1 dot content, so it will basically give the whole content of this particular memory. Again, I'm doing a second episode, so it will return episode object as well. So say I'm creating a second episode. Here again, I'm putting some data here. Failed to fetch live traffic data, extend API time dot. Here user asked about weather forecast for Paris this weekend. And also third episode. So I'm putting it as a failure because there was a failure observed. Importance is I'm giving a 0.8, and then memory remember episode is API where I'll again dump the episode content. So this is the episode content. User confirmed booking for Paris hotel on Saturday. So if you can see here, so basically this and this looks like somewhat related because they are in the talking about the Paris. So here outcome is also success. Importance is 0.9. You can print the episodes e1.id, 2.id. This basically prints the ID of those each episodes. And then, as we mentioned, we can link the episodes as well. So if you see, remember concepts.md, you can always do a linking of the episodes via ArongoDB edge. So here you can mem.episodic link episodes is the call. So every like say for any memory you want to access, right? Mem.episode, mem.reflective, mem. The semantic, all those things are possible because you have file different layers. You can call mem.episode, mem.reflective, and this is for creating the episode directly. Mem.remember episode, dumping the data into the DB. So any other activity you want to do within the episodic memory, you will be using mem.episodic. So mem.episodic link episode is a function or API that I'm using, and I'm saying e1.id and e3.id because e1 and e3 are related to Paris, so I can link them. And the relationship, the edge name that I'm giving is led to booking. So I because of this, this happened. So led to booking is the relationship I want to give between these two episodes. So to do semantic search, I can do map episodic dot search. So and since it's episodic memory, you have to give a your strings. It's a semantic search, so you have to give a string here, and you have to give a top k3 here. So because of this, a semantic search will happen, and everything related to Paris Paris travel plans is there, right? So they will get displayed here. So the top K3, only 3 items will come into picture. Maybe probably for this, and this will give a higher confidence, and maybe this will get a lower confidence because this is something irrelevant. So semantic search. So let's go to before going into the detail, right? So let me see the API reference as well for this particular example. So API reference. So you have for episodic memory, get by session, get by agent, get by outcome, get high importance. So these are 4 APIs for filtering, and in the graph case, you have link episodes, get related episodes. So these are the 2 uh, APIs are available in your graph. So graph way. So I guess this episodic search you would have not seen here. The reason for that is it is not related to episodic memory alone. This dot search is related to any of the this dot search operation is available for also all the 5 memory that we have. So but right now you are asking it only to do it in episodic memory. So basically this classes are imported by our base class. So for that you have base memory store is available. So this will have store, retrieve function, search function, update function. So it has those functions and delete function. So this base class is basically base memory store is imported by these classes. So all the functions that this is available here will be available for these functions. So I'm using the search function which is available in the base memory store, but I am using the episodic. So episodic is, it will use only the episode memories, not any other memories. I'm not doing search across all the memories. I'm doing search across only the episodic memories. I have stored 3 episodes and I'm doing a search in those 3 episodes. So next, episodic get by session ID. So as I mentioned, get by in the filtering, you have get by session ID is available, get by agent is available. So those get by outcome is present, get high importance is present, get high importance. So get high importance is present. You need to give a threshold here. So whatever beyond the threshold, only those things will come first, highest the first. So and also I have a episodic get related episodes. So get related episodes is a graph related transaction. Get related episodes, you will give a memory ID and it will give you all the linked memory IDs. So here you will get a node.get content. You will basically print the content of it. So let me just run it. So again, to remove the episodes, you have a delete function. So mem.episodic.delete. You can do e1.id, e2.id, e3.id. This is for a deletion purpose. So whenever you don't want it, you can delete it. So let me run this examples one by one. So let me go to examples folder and Python example episodic.py. So let me just run it. So it is not trying to connect to the maybe databases. So yeah, so it has stored 3 episodes. These are the IDs of those episodes. As you can see, these are the 3 IDs of the episodes. So now first is a semantic search. So you have done a semantic search on those episodic memory. It is a semantic search on those episodic memory alone. Paris travel plans. So as you can see, 54%, 54% confidence is for the user confirmed booking for Paris hotel on Saturday. Next is user asked weather forecast about Paris, and the low confidence is for a failed fetch live traffic. So this is the semantic search output. So here next is by session ID. You would have given some session ID, and for that session ID, what all things are present, you have it here. And also you are searching for the outcome failures, and the failure related things are present here. And high importance 0.9, 0.8, that is 0.9 is for a hotel booking, and 0.8 is for a failed traffic data, external API timed out. And related to A1 via ArrangaDB, so user confirm booking for a Paris hotel on Sunday. So this is for get related episodes. You gave e1.id. E1 was this particular event. Users asked whether in Paris, and you were asking for a related episodes. Any other related episodes are present or not? You are just asking it, and you got E3 as a output. User confirmed booking for Paris on a hotel on Saturday. So this is the E3 content, and you have a deleted. So deletion is success. So this is a episodic memory example. So let me go to some other example. Let's me go to the semantic memories, the second memory type. So again, the top things are remain same. No other changes in that. So here, here I'm storing agentic. Again, I'm creating agent memory object with OpenAGI and the configurations. Here I'm storing a known fact is the function. So in the previous, it was a remember episode, whereas in this case, it is about a no fact, mem dot no fact. So you need to provide a triplets here, subject, predicate, and a object here. So Paris is capital of France, confidence is 100%, France is a member of European Union, Eiffel Tower is located in Paris, uh, museum is located in Paris, Louvre Museum is located in Paris, Seine flows through Paris, Napoleon was born in Corsica. So these are few facts that I have stored. You can give a source as well, like an encyclopedia or any string you can provide. And also known fact, Corsica is a part of France. So these are the known facts, the the world truths we have stored in a memory, the semantic memory. So let us search the semantic memory. So right now I'm using a mem.semantic. Earlier I was using mem.episodic.search, whereas right now I'm doing a mem.semantic.search. It means it will search only in the semantic memory data that we have stored. So European capital, famous landmark. So if I say this, from it will search only this particular content. It will not go and search the internet. So it will just take this data, and it is trying to get a top k as a 3 here. So those details will be printed. So this is the semantic search. Then semantic get by subject. So let us check the API reference. Let me go to semantic memory store. So in that you have a triplet lookup, get by subject, get by predicate, get triplets, and get above confidence. So these are the 4 functions present there. And also to know the knowledge graph traversal, get neighbors, and find path. So these are the 2 APIs present for the knowledge graph traversal. So here it will run semantic get by subject. So you are giving a Paris. So if you see here Paris, so France is here. So it should print the France. So mem.semantic get triplets, Paris is capital of. So Paris is capital of. The subject was present, the predicate is present, the object will come as a output of that. And mem semantic get neighbors. So what all are the neighbors present for Paris? Direction, outbound. So outbound, inbound is basically the arrows of direction. So Paris, outbound is like a from left to right to the France. So France should be the output here. If you do it inbound, then these are the 3 things. So Paris, basically it's the object, it becomes the object whatever you have given here, right? If you make this as inbound, the Paris here you have mentioned becomes an object, not a subject. So right now it is outbound from Paris, what is going out, so France. And if it is inbound, these 3 will be result of it, like Eiffel Tower, Louvre Museum, and Seine River. So that is outbound, or direction you can mention outbound or inbound for get neighbors. And also we have a find path. So again, yeah, so you need to check the get neighbors API reference here. Get neighbors entity direction you need to provide, whereas find path you need to give from entity to entity, and you will get the shortest path between 2 entities in RangoDB. So right now, for example, I'm giving a Napoleon and European Union. So if you see here, Napoleon is here and European Union is present here. So it will try to derive any, the how it can reach from this to this in a shortest manner. So it will go to Napoleon, then it has a Corsica. Corsica is present here. It goes to France. France, anywhere it's present here. Then it will European Union is present here. So basically, you will get, yeah, whether you can derive from Napoleon to European France, European Union or not. So if you get it, so you will get the output here. And also similarly, I can do a delete operation. So let me run this example. Let's go semantic.py. So the DB connection is getting established. Yes, so facts are stored. So European capital, famous landmark. So you are getting Paris is capital of France. Eiffel Tower is located in Paris. Seine flows through Paris. So these are the semantic search result for this particular string that you have. So subject ID Paris, the Paris is capital of France, so you got a triplet. You give a Paris as subject and you got all the predicate and the object. So get triple Paris is capital of. So if you have subject and predicate, you can check the object of it. So the neighboring of Paris, so it's a outbound, so you will get a France. So basically here you get a Paris and outbound, right? So Paris outbound is France. So if you say Paris inbound, you will get these three as an output. Next, Napoleon and European connections. You are traversing and you are getting a Napoleon, Corsica, France, European. That's what I have explained in this data here. So next is a deletion. So this is a semantic memory, and then we have a. Let's go to the third memory, procedural process. You need to give some process. So here similar, send email is one process that I'm creating. So learn procedure is a function that you need to use, API you need to use. You need to give a name to it, you need to give a description, and you need to give a trigger conditions, and you need to give a steps. So this is according to the example, the readme that we had, right? The concepts. So the procedural memory, name, trigger, condition, steps, success rate, use count. So those details you need to provide here. So now you have registered these three procedures, you have stored these procedures. For sending a mail, what needs to be done? Validate recipient. Again, these are the procedural steps. It has to be list of steps. The list is here, and you have three things you need to provide. So what is that? The action, parameter, expected outcome. So you can check uh, the concept.md. You have to provide a procedure state. It has a ordered, and you need to provide these three as a dictionary. So that's what we are doing it here. To validate recipient, field 2 outcome of expected outcome is valid email address is required. The compose body, email body text is required. It has to be composed. Call mail API 202 is the accepted one. Expected output, confirm delivery. So a delivery ID is has to be returned when you call the send email. So these are the procedural steps. So to book the flight, again you are calling a learn procedure, book a flight. You are giving the details to book the flight. Then you have two procedures you have created, and record execution. So right now you are doing a simulation here, meaning let's say this has the agent has done this activity and you are putting it in a success. So I'm putting some success here. So send email ID, so this is the send email ID. um, Send email ID, send email is uh, the procedures that you have stored, and for that ID you are giving two successes and one failure. And for one other flight booking, I have given a success. Basically for email sending, two is success, one is failure, and flight booking only one, we have done a simulation, and one is a success. So right now you can do a semantic search for this procedural memory also, similar to other memory we saw semantic search, right? So here also we have procedural search, send a message to someone. So whenever I see this send string top k3, so I'm just trying to see which process it will get selected. So and then this is one. Let us see the output of it. So when I do a semantic search, send a message to someone, top K3. So here basically send a message to someone, send email has a 32% and book a flight has a 24%. So it is a semantic search. And it is mentioning about the steps also, how many steps are there in each. It is just mentioning that. So trigger condition search. So trigger search, user wants to fly. So search by trigger. So trigger conditions we have, right? So this is the trigger conditions. This is the trigger conditions. So here the trigger condition is user asked to book a flight, destination provided. If these are the trigger conditions, right? So then it is like it's about a fly. I mean, that will be used for a semantic search. So search by trigger. So you are directly targeting the trigger content, and you are doing a semantic search. User wants to fly somewhere. So let us see what is the output we got. User wants to flight somewhere. So book a flight. User asks to book a flight and destination provided. And this is the next one. So send email. So since highest is the first one is the highest priority, we can use this particular procedure to execute. So this is the semantic search of a search by trigger. And you have a get by name also, like you can again check the API reference, procedural memory, execution tracking, record execution. So whenever you want to update, that's what we have used in the record execution here. So whenever you want to say success or failure, you will be using that API. Then filtering, get by name, get top procedures, get search by trigger. That's what we have used, search by trigger. And yeah, and there is a search as well. So that's what we have used here. And also we have a certain other thing, get by name is also here, and we have a retrieve. So this retrieve and retrieve we haven't seen earlier. So if you go to our API reference, so as I showed, base memory, it has a store, retrieve, search, and update and delete, right? So you have a retrieve function here. You need to directly give the ID here. Whereas search, you give a query string. In the retrieve, you have to give a ID. So here I'm doing a if fetched mem procedural dot get by name send email. So send email if this name exists, get by name, right? So if this exists in the procedural memory, if fetched, then retrieve the ID of it. So you are getting basically retrieved ID, and you are doing some operations here, get or dumping or something like that. So this is why this is what you can, these functions you can use for I mean any those four functions you can use it for all the DBs. Only specific APIs related to those will be provided here, and that alone you need to use in those particular memory. So top procedures, get top procedures. So you just have to give a limit, so it will get you the top procedures present. So let me just run it. So yeah, I have already run it. So trigger search. So user wants to fly. Yeah, we have seen that. Send email stat user count 3, use count 3, so success rate 0.67, validate recipient. So basically it was this. So send email, right? So you are trying to print all the steps. What all the steps? Steps: validate recipient, compose body, call mail API, confirm delivery for send mail. And top 3 procedures: book flight is having a success rate of 100%, and send email has a success rate of 67%, because one was a failure that we have recorded. And you can do a deletion as well. So this is the procedural memory. Then I'll go to the reflective memory. So let me run the reflective memory. So let me show you here reflection. Yeah, so I have created one episodic memory here. Agent provided weather forecast using a stale cache data from 6 hours ago. So this was one data, scratchpad data that I want to store. Session is 77, weather agent, failure, 85% important. So I'm just storing one episodic memory here, and then I'm creating a reflective memory. So reflect is the API call that you need to call to store the reflective memory. So you are giving a content, provide stale data without warning degrades user trust. So this is the content. The lesson learned from is always check the fresh cached cache freshness before serving the forecast. So improvement suggestion: add a cache TTL check before responding. If stale, fetch a live on a or a warn user. So this is the improvement suggestions, because the reflective memory, as we have seen it in README. So reflective memory, lesson learned, improvement suggestion, source episodes, confidence. So these things are required, right? So that's what we are giving: content, lesson, improvement suggestion, source episodes, and confidence. So this is the source episode. Agent provided weather forecast using a stale cache data from past 6 hours. So this is the one episode, and this episode led to this particular reflection. That's what we are giving a source episode. So confidence is 95%. So next, one other reflection is a silent failure are harder to diagnose than explicit errors. So I have a one other lesson learned, but I don't have any source episodes here. As you can see, source episode is not there. Again, there is one other lesson learned: user satisfaction drops when agents don't acknowledge a limitation. So this is one other episode without a episodic memory linkage. So here, search data quality issues, data quality issue. Whenever you search like this, again you are doing a semantic search for reflective memory. So let us see what is the output you got. Data quality issue. Be transparent about data freshness, uncertainty. Log all data sources, fallback explicitly. Always check a freshness before a serving. So this got the highest confidence. Now we will do an simulation. Basically, I'm increasing the count of the applied count. So there's a API known as mark applied. So this mark applied will mark applied. So it will basically increment the applied count in Postgres SQL. So it will be just do an +1 to the already available mark applied count, and also syncs the new value to the ArangoDB. So I'm just doing increment for the R1. So R1 is we have this, and R3 is this, but I'm not doing any increment to R2. So when you check most applied reflection count, so you have to do a get most applied. You are just limiting it to 5, and all the right now only 3 reflections are there, so you will get a 3 reflections output, and the 2 is for the R1, 1 is for R3, and 0 for R2. So next, similar to that, we have one other API, get from episode and get reflections for episode. So they tend to give similar output. So get from episode. So get from episode, you have to give episodic ID, and you will get a list of reflective memory. So all reflections that site given episode as their source. And one other function is for a graph traversal, get reflections for episode. You need to give episode ID. It will give a list of dictionaries. So basically, it will do an ArongoDB outbound traversal over episodic reflection. So whenever you link the, in R1 we have linked the so for R1, we have linked this episode, right? So it will create an edge, and that is outbound. The edge name is uh, episodic reflection, which is of outbound. So this API basically search the all outbound traversal with this particular edge name. So that has given the output of that looks very saved for now, because always check cache freshness. This is the R3 reflection, sorry, R1, and this is also R1 for a given episodic memory. So next API we have is a confidence based filtering. So you can always check get above confidence, some threshold you can give, and also you can do a delete operation. So confidence based filtering is there, and the data operation output is there. So this is the reflective memory. And now let's go to the example, reward memory. So let me run the reward example. So in the reward example, so you have to create a tuple. You need to create a state, action, and a reward. So we are creating some state actions here as a list of tuples. So battery level is critically low. Recharge now. For that, we are giving in 1.0 as a reward. So its battery restored is the final outcome. Battery level is critically low. Continue task -1.0. So if you do this continue task, -1.0, so you are negatively rewarding because battery is going now. You need to recharge it. So the action can be a device shutdown. So battery level is critically low. Recharge now. Again, you are giving an 1.0 as a reward. So user is idle for more than 5 minutes. Send summary. 0.8 reward. User re-engaged. So this is basically, again, user is idle for more than 5 minutes. Do nothing. So if you are not doing anything, so then again you are giving it a reward of minus. And external API rate limit reach, back of 60 seconds, and you are giving a 90% the 0.9 as a reward. And again for the same thing, retry immediately. So if you try immediately, because the already rate limit is reached, if you are retrying immediately, you are getting a negative 0.5%, 0.5 as a reward. And if it is again, so back of 60, so I'm giving in 90% reward. So similarly, task queue is empty, enter standby. Task queue is empty, hold for a new task. So for this I'm giving in 0.5 as a the reward, and for this 0.2 as reward. So basically I have a list of state actions. So state, action, reward, and what is the final outcome of it. So this I am using a record reward as a API, and for that you need to give state, action, reward, and outcome. So those values are present from this particular list. So I'm creating a policy, and the namespace, the policy and the put a namespace, I'm creating a default, and I'm just putting it into the reward memory. So that all the IDs I'm trying to collect here, and record state transition in ArangoDB. So I'm just trying to uh, I'm just trying to do a simulation. So ID 0 is nothing but this particular the task, and id2. So this is nothing but this particular task. So recharge now, action in recharge now. So I'm just doing an for recharge now, I'm just doing a simulation. So basically I'm just recording the state transitions. So best action for similar state. So device battery is almost empty. This is a query. So what needs to be done? So get best action for this particular query. So query state, and what the policy that you have chosen is a default one. You can create anything, battery management or anything policy name you can give, but I'm checking it in default policy. So get best actions. So let us see what the output would be. Best action, device battery is almost 0, so action is recharge now. Average reward is 1.0. Why it is 1.0? Because you are given 1 and 1 divided by 2, such things has happened. So 1.0 is a average reward now. So next is so this is for getting an action. What is the action, and what is the average reward result? So next we are doing a semantic search over the states. So reward dot search is the API throttled too many requests. So this is my query, and I need a top 3 actions. So this will do a semantic search. So this was again a best actions. Again, it was doing a semantic search sort of query. So here so API throttled many requests. So let us see what happened. So API throttled, so action back of 60 second, retry immediately. So in that, this it's a semantic search, right? So not the best one. So semantic search is done. So 56%, 56 percentage, and 52 percentage for this particular semantic search query. So you got all the search result for this particular query. So again, we have a per action state. So what you are doing is get action state default. So basically you are trying to print all the actions available in default namespace. So you can check always the reference, the API reference. So vector search for top k. So basically get best actions. So what this find best action for a state similar to state description. State description is your query. It does a vector search up to top k. The top k also you can send. Filter to policy, so falls back to all the candidates if none match. Group by action, compute and average reward per action, return action and average reward. So this is the task of this particular API. And you have one other function, get action steps. So let me see whether I have used it or not. No, so I don't have that example. So these are other APIs. So next, get policy summary. So you will get the summary of all the default policy that you have created. So that is nothing but action stats policy default. So recharge now, what all actions you have stored, right? All those summaries you will get it. So next is top 3 reward memories. So top 3 reward memories, get top rewards. So that top 3 reward is here. So top 3, the one is recharge now, and back of 60 second is. If you have linked two memory IDs, that's what we have done in the top. So we have done a record transition from ID 0 to ID 2, and action is recharge now. So since we are just connecting two IDs, you can query also the two memory IDs using get successor state. So you need to give the source ID, and you will get the linked other IDs. So get successor state. So you have to give one memory ID, and you will get a list of dictionaries. So it's basically a ArangoDB output traversal. All the reward states reachable from this node is what you will get as an output. And also we are doing a delete operation. So this is about the reward memory. So let us create a simple example of agent code. We want to use certain of this memory, and we just want to project an reference example. So we'll check that. Yeah, before going to that, I just want to show you what if your embedding is not an OpenAI embedding. You don't have OpenAI APIs. You want to use something like Gemini or any other embeddings you want to use. How to use it? So have this particular file. So here I have a configuration. I am creating an embedder provider, and you are giving an OpenAI key, and that embedder also you can provide as an embedder. In general, in our earlier example, we were let me show you the how it was used. So CFG I was passing, and I was passing an OpenAPI key. So by default, it will take an OpenAI embedder model. If you want your own embedding model, like you want to choose your own embedding model or something like that, so you can give an embedder itself as an example input to the agent memory. So here still we are using a open API model only. So in next example, so in this example, as you can see here, so you are creating a client from the open API key. So it could be for Gemini also. So you can use the Gemini SDK, and you can create your client, and from there you can create a function, and that function you can provide as an input to the embedding provider. So here embedding provider, I directly give a API key. If I give a API key, it by defaults to OpenAI. If you have any other provider, you just have to create the function and use the client that you have created, and this embedding model should return the embedding. So based on GenAI, let's say if it is a Google Gemini, how it returns the embedding, you need to derive it, and it has to give it as an output from this particular function. So that function I'm passing to the embedder provider, and then I'm passing this embedder as an embedder model for a agentic memory. So basically agentic memory, if it has an embedding function, it will call the embedding function. If it has an open API key is being sent, it will then use the open API key embedder. So this is how you can use a different custom embedding model. So now let's go to the example implementation. So let me just come back to yeah. So you can see a document analysis agent. So let me just open that. Okay. So here we have a directory structure. It is basically this example, what it does is it uses again our agent SDKs and our memory grid libraries to we focus on a like simple document analysis, where agent uses agent grid library for storing and retrieving different memory of an agent by breaking text into sentences and store them with episodic and semantic memory. Right now I have taken only two examples, episodic and semantic memory, and later retrieve it. So the folder structure, nodes, spec, and deploy. This is very standard that we used to follow. So spec will contain the spec files for registration. Nodes will contain the Python of the agent, Python code of the agent, and deploy and run for running the workflows and workflow registration. So let me just register the agent, and the agent Docker is already built and push. I will not do that, or else it will take some time. So let me do an deployment of agent. Agent is deployed. So let me just check. So yeah, the doc analysis agent is present, and let me register the workflow, and let me deploy the workflow. Okay, so all things are done. We just have to run the input. So before that, I just want to show you what this agent is actually doing. So let me just go to nodes, and let me use the sample doc agent. So here uh, so basically we are using agent fs dot class. So here we have again provided a small library for this example. So let me just show you that agent fs. So here we have a small of library, so that is being used here. So git back to checkpoint every processing stage as an immutable commit. Any past versions of any document is recoverable via its commit hash. So basically it's a version file system library backed by the git standard git. So we are using an episodic memory and semantic memory just to as an reference example, where each processing runs is logged in as a timestamp episode with an outcome and importance score. And semantic memory, we store it as a subject, predicate, object, triplets extracted from the document and are stored in the knowledge graph. So let us see the example. So I'm importing everything. So whatever is required, I'll just import here memory config or AngoDB config. So all these things I need to place it, right? Earlier I was using an in the examples, so I was using a dbconfig.py, but I cannot do it here. I need to do a registration. So those registrations are done in the registration file. So I'll just show you that. So if you go to prompting, sorry, persona, if you go to config, the parameters, so I have a memory config and I have a fs config. So these are the two variables I'm using it inside my code, and I'm passing all those details. What the db.config was doing, the db.config was basically reading from env, right? But here yeah, the when I'm registering, so I'm basically registering with all these values, v8 details, rango details, postgres and redis details. So all these are pushed from the env to a registration. So and those values I'm reading it in my agent code. So once I read the content, I'm calling those individual classes to take the dictionary content of those the registration, and they create their config. And so yeah, that's what is happening here. What is a model embedding model? Which embedding model I need to choose? All those are again registered here. So let me just embedding model type, embedding model, and embedding model block ID. Which one I need to choose? Which block I need to choose? So in the models integrations models, so I might have multiple models, but in that I need to choose the one model which has with this block ID. So that's what right now I have only one block. If you have multiple block, you can basically instruct which embedding model to. Let's say you have multiple embedding model, or you have multiple, one is embedding model, one is a LLM for a a general conversation. So it is a list, right? So which one in that to choose for embedding? So that's what I'm saying as a embedding block ID. So that is the thing. Right now here only one block ID is present. That's what I'm asking it to choose. And its API key is present in parameter. API key is present in the parameter. So in my code, so I'm using that, which is the embedding model from this particular if and else conditions. And then I'm creating an agent fs where I'm creating some paths. Right now I'm not reading anything from the except the maybe few things. Let me just see the fs path, author name and author email. This is for commit we are using it back, right? So we require a committing which requires author name and email id and path. So that's what I'm initializing it, agent fs. And then we are creating a memory config. We are passing v8 config, rango config, postgres config, redis config, embedding model name, and I need talk details. So all those things we get it from the rod I mean the agent registration content, and I'm passing it as a dictionary key value pair to this particular v8 config. So now this is the memory config, and I'm creating an agentic memory. So since I know that it's an OpenAI, I'm just trying to pass the OpenAI API key directly here. If you have anything else, like I was giving an example of any other model, so you need to pass an embedder object, and in the embedder object you can pass your own function of your LLM model. So whenever we get an inference request, so basically we take the text out of it. Whatever text we'll check the text, we'll get the text out of it, and also we'll collect the document ID details. And from there we will try to create a commit the raw document. So first we commit the raw document. So whatever the text we get, we'll dump it into some folder, and we'll do an fs write. So it will give a hash, and we are just going to go in, we are just putting it in version log append, and all the details about that stage is raw, commit is h1, this the it will pass the commit, and what is the path of the file. So it is just the version log which is holding a version log is a empty array now of a dictionaries. So next I'm going to do a commit sentence level chunks. Basically this raw text can have too much of content, so I'm going to create an chunks. So for chunks related details, I'm going to I'm going to again commit. So basically I'm going to split the whole text into chunks, and those chunks one by one I'm just dumping it into a chunks.json file. So whatever the splits I got, right, so I'll just dump it into a chunks.json. So what the split sentences does, let us see in the bottom. So split sentences, what it does, wherever there's a question mark or a dot or a exclamation, so basically it will break down the sentences into the whenever it sees this, it will basically chunk them. So it's a very simple chunking. So you can always complicate this chunking process with overlap and all. Right now I'm not doing it for a simplistic example. So we are just writing those chunks into this particular chunks.json, and again we are doing an commit. And once the commit we did, we are just putting it in a version log. Again, the stage is chunked. Earlier the stage was raw, and now stage is chunked, and commit is h2 and a path of the chunked file. Then we are trying to extract the facts. So from all whatever the chunks are there, right? So the whatever the chunks we got, we are trying to extract some facts from it. Basically, we want a key, the to put it in memory. We are trying to extract some facts, semantic memory. We are trying to extract some facts. So here you can check the extract facts. um, so extract facts, here is a function. So basically if it sees is or has, it's a very simplistic. So again, to make it for a practical use, you can always check with the LLM. You can use a product for production, you have to use the LLM. But right now I'm using any simple patterns. If there is a is, or, has, was, were, can, contains, any other anything, these are content, right? Then I will say the left side is a subject and a object. So that's what I'm trying to do it here. So subject, predicate, object is being you know we are using a v here, re here. So re basically matches this pattern and get subject, predicate, object, and the raw sentence of it. So this is what is written from the script. So extract facts, and that facts again we are putting in analyze.json. All the facts we are dumping it into analyze.json, and then we are doing a commit operation, and that commit operations log is here. Stage is analyzed, commit is ht, and path is analyzed path. So now give the full immutable audit trail for the file. So basically we are just going to for c in self fs.log, the file path is unliced path. Unliced path is this particular JSON. So we are trying to get all the hashes. So fs history c dot hash, short hash is c dot short hash, and message is c dot message, whatever the commit message was there, and date, commit date. So we are just taking the fs dot history. And right now the episodic memory, we are going to do an episodic memory. Remember episode, I'm just randomly calculating some importance. So right now we are doing something here, but you can always check the LLM here. I want to store an episodic memory, and the episodic memory storage API is this. It requires some string, it requires session ID, agent ID, context, outcome, importance. So you try to get the relevant data from this input. So that's what you can ask the LLM. Maybe LLM can help you in getting those details. So right now the episodic memory processed document is the document ID. So that's what I have extracted here. And then the sentences, how many sentences we have in that, that's also I'm trying to put it as an content in the episodic memory. And also I'm going to put the number of facts. So how many facts we are able to extract from the sentences, and facts accepted, and commit the fs commit. So h3 of 8, so which is the third commit, h3 of 8, we are just dumping it into a episodic memory. So so session id, agent id, and all I'm providing it here, and some key value pairs. So free form key value pairs, so doc id and fs commit, I'm putting it here. Outcome is a success, and importance is some random value here. So now next, again I'm creating a semantic memory also, um, so that I have a, since I have a subject, predicate, object, right? Basically I look through all the facts that I have derived, and I'm just dumping it into known facts. So you have to get a subject, predicate, object, and raw sentences. If not available, we are getting a empty, and the source is nothing but the doc id. So here let us do an recall, basically retrieval will do. So whatever the input we have got, from that I'm just trying to extract the last 256 character, I mean the first 256 characters only, and that is my query now. And I'm going to check the dot search operation. So it's just a reference example. I'm doing a search operation, which is a semantic search. So I'm passing the 256 characters of the input only, and I'm just querying it. So I'm trying to take a top k3 from the episodic memory and from semantic memory, and that's what I'm returning. So those past episodes and the related facts, right? So I'm just returning it. So this is the code, simple code, just to show you the usage of those agents, how to how you can directly take this as a reference code and implement your logic for your agent code. So let me just run it. Before that, let me just show you the input. Deploy and run workflow input. So right now, yeah, this is my first input. This is my first input. Python is a high level programming language. Python has a large standard library. It's something related to Python. Next is also something related to Python, and third time it is something related, very olive oil related. So when we send this input, so basically it will create a chunks and it will store it, and it has a document ID. I guess it has some document IDs. So payload, some document ID I'm sending, and this is one other document ID. So B39, B38, different document ID, but it has again a different content. And as you have seen, to the retrieval example, what we were doing is we are taking the query itself, like the input text itself, as an querying, right? So whenever we send the first input, basically it will first input, it will take this some 256 characters, and it will try to search for semantic segment, semantic as well as a episodic. Then when we send the second input, right now this is getting stored in semantic and episodic, and now we are sending the second document. This also will get stored, and when we again query this, right, so we might get the content of this these episodes and also this episodes, so because they are related to Python. But when we do it for olive oil, when we send the third input, olive oil is entirely different. So but it will search only related to olive oil. You should not, I mean, even though you get it, it should have a lesser because the about two documents were related to Python, but whereas this related to olive oil or health related. So you should get only the contents related to olive oil, not related to Python. Even though you get it, you will get it with the lesser confident. And the search, since I'm using a search, it will do a semantic search. So let me run the inputs. So the first input is sent. Yes, we got some output. What output you are getting is, you are getting all the facts in this. After chunking it, whatever individual chunks are there, right? From that you are trying to extract a fact. Object, predicate, raw sentence. Subject is Python. Basically, I'll not explain again. So basically, it's taking wherever is, are, has, all those things are there, right? It will break it in. It will give a facts. So once you have all the facts here, then you have fs log, basically what all the last log it has done, date, commit hash, commit message, and also the short hash of that. So totally 8 facts are there. Those details are also was there in the code. So it is given the fs log. Related episodes, so the process document, 8 sentences, 8 facts extracted. Fs commit is this, and the related facts. So Python has a larger standard library. So basically this is the related fact, related episodes. So it is a version again. So now again we are sending a second input. Second input also you will get some facts in it, and the related episodes you are getting a process. These are the two related episodes which has semantic similar, and these are two facts. So Python is widely used data in science and machine learning. TensorFlow has a Python binding. So these are the two facts you got for the second input. The second input was related to Python is widely used in data science, and TensorFlow is a deep learning framework. So maybe it has taken this first 256 characters and tried to do a semantic search. So it gets the facts. So all the related facts you got. And for the third, so when olive oil is queried, so let us see how it behaves. So now process document is related episodes, related facts. So you got only the related to olive oil. You have not got anything related to the Python. So uh, it's a simple example, so we are not done and very complicated. So our main idea is how you can utilize this agent code, and you can how to utilize other memories. So yeah, this is the example, reference example. You can modify this example to get any of other memories. So we have just showed only the episodic memory and semantic search memory. So that's it. So this is the 5 different memories example. So in the next video, we'll see some other implementation of memory usage. So thanks for watching and keep supporting us.